We're going to be looking now at how to graph these rational functions. Take a minute here and pause the video or go to OneNote and copy down these steps. And then we're going to do 3 examples of these. In our first example, let's take the rational function f of x is equal to x squared minus x over x minus 1. We looked at this previously, but I want to follow these 7 steps. The first step is to factor the denominator to determine the domain. The denominator is already factored, and we know that the denominator can equal 0, so the domain is all x except 1. Then we factor the numerator, which again, we did in a previous problem, and we see that the common factors that cancel. So if the zeros of the common factor become the x coordinate for holes in the graph, so we know there's going to be a hole in the graph where x equals 1. When we plug in that 1 to the simplified equation of f of x simplifies to just x, we see that our hole is going to be at 1, 1. We can use the remaining linear factors in step 3 to find the vertical asymptotes, but there are no remaining linear factors. Then we can look at the degree of the numerator and the denominator to find horizontal and oblique asymptotes. Again, it's reduced, so there is no denominator. If 0 is in the domain, which it is, we can find the y-intercepts by plugging in 0 for x, which gives us the point 0, 0. And then we can find x-intercepts, which again is going to be 0, 0. And then we can just plug in additional points to see that our graph is just going to be a line with a hole in the graph. But that's the same graph we did earlier following these steps. Let's follow those same steps and look at something a little more complicated. If we have x squared plus 1 over x squared plus 2x minus 15. Step 1 tells us to factor the denominator. When I factor the denominator, I get x minus 3, x plus 5. This tells me that the domain includes everything but 3 and negative 5. Moving to step 2, we factor the numerator, which in this case cannot be done with real numbers. The zeros of the common factors are the x coordinates of the holes, so there are no holes in the graph. But we can use these remaining linear factors to create our vertical asymptotes. So if we come down to our graph, we know we're going to have a vertical asymptote at 3. So I can go ahead and sketch that, and at negative 5. Again, this is helping us create a generalized graph. Step 4 tells us to look at the degree of the numerator and the denominator. Notice here, the numerator and the denominator degrees are equal. So we have a horizontal asymptote is the quotient of the leading coefficients. So we have a horizontal asymptote at y equals 1. Step 5 tells us to look for the y-intercepts. 0 is indeed in the domain by definition. Where x is 0 is the y-intercept. So when I plug in 0, I get negative 1 over 15. So when x is 0, y is going to be negative 1 over 15. Step 6 says to look for the x-intercepts. That is found by setting the numerator equal to 0. But we already know this has no real numbers, because if we subtract 1, we're going to get an imaginary number. So there are no x-intercepts. And then if we just take a couple of other points, for example, I took 4 and plugged it into the equation, and I get 1.889, which is going to put me up here somewhere. And then I plugged in negative 6, and I got 4.111. Somewhere up here. And so what you're going to find if you plug in several points is you end up with a graph that looks like this. As a last example of following these steps, let's consider x cubed plus x squared plus 2x plus 2 over x squared plus 9. The denominator can't be factored, step 1, so we know the domain is all reals. This tells us then that there's not going to be any vertical asymptotes or holes. Notice, however, that the numerator has a degree of 3, which is equal to the denominator plus 1. This tells us that we have to divide to find an oblique asymptote. I'm going to trust you to go back and try the long division if that's something you need practice on. But what you'll find is that the oblique asymptote is going to be the line x plus 1. So if I come over here, my y-intercept for my oblique asymptote is going to be 1. And I'm going to have an oblique asymptote that looks like this. If I want to find the y-intercepts, I plug in 0 for x, which leaves me with 2 on the top and 9 on the bottom. So where x is 0, y is going to be 2/9. We also need to be able to find where the x-intercepts are. And to do that, we're going to set the numerator equal to 0. And this looks like a difficult value to factor, but if you'll notice, if we plug in -1, it's pretty easy to see that that's going to reduce it to 0. Since x gives us that solution, we can then use synthetic division to reduce this further. Remember, we drop this down, multiply, add, gives us -2 and 0. So this tells us that we have a factor of x plus 1 using this 0. And then our other factor is going to be x squared plus 2. This has no real solutions. So that -1 is our only x-intercept. Remember, we said it can cross that oblique asymptote and then we'll eventually approach it. And if you plug in some other values, what you're going to find is your graph ends up looking something like this. Again, these are rough sketches based on a few points.